Today we're going to be discussing 9.2, but before we get into that, we're going to do a quick little practice from our last lesson, and we're going to look at the infinite sum of this sequence here. So we're going to look at this series. The sum, this time our index is going to be j. So from 1 to infinity of 34 times 1 over 100j. And so what we want to do is we want to try and do this without a calculator. So we want to start, okay, well, what are the first few terms in this series? So we know essentially, okay, what if j is equal to 1? J is equal to 1. What's our first thing? This is going to be 34 over 100. Plus, if j is equal to 2, we're raising 1 over 100 to the second power. We're squaring 1 over 100. So this is 34 over 10,000. Plus, if j equals 3, 34 over, I think that's enough zeros there, 1 million. And it just keeps going, going, going. Now, just like the ones we did in class the other day, or you watched the video on, we want to write this as a decimal. This is 0.34. This is going to be 0.00034, 0.00034 plus ... You might see that when we add these all up, we're going to get 0.34343434 repeating. So we just keep repeating the 34, 34, 34, 34, 34, 34, 34, 34 over and over and over again. And we can try and figure out what that is as a fraction. And if we do, we end up with this is 34 over 99. Okay, so there's our sum without a calculator of that series right there. Now we're going to go back to Jack. We're going to see what our good friend Captain Jack is doing. So Captain Jack has exactly 30 seconds to solve this following problem, or the roof shield will open up and the cavern will be filled with snakes and water. Ugh. All right, so here's the problem. On the entry stone, input the number that is the sum of the first 99 whole numbers. What I want you to do right now is I want you to try and figure out, pause the video if you can, see if you can figure out the fastest way, potentially without a calculator, to add up 1 to 99. Okay, so if we're going to add up 1 to 99, the way I would think about doing this is, okay, if I were to list out all of these numbers, I have 1 plus 2 plus 3 plus 4 plus ... plus 97 plus 98 plus 99. Okay, those are all my numbers. What I'm going to do is I'm going to pair my numbers off. So if I pair up 1 and 99, if I add those two together, that's going to give me 100. But at the same time, if I pair up 2 and 98, that's also going to give me 100. And then 3 and 97, that gives me 100. And what I'm going to do is I'm going to continue to pair up all of my numbers. And by doing this, I can pair up all my numbers so that they're in groups of 100. I can count up how many 100s I have. When I do this, I need to be careful because there is one number that's not going to pair up. The number right smack dab in the middle, 50. 50 is not going to pair up. You're going to have 48 and 52, 49 and 51, and then 50 is smack in the middle. So when I do this, I'm going to have 49 pairs that add to 100. And then I'm going to have 150 left over. But that's still not too bad. 49, 100, 100s, that's going to add up to be 4,900 plus a 50 left over, that gives me a total of 4,950. All right, so 1 to 99 added up to 4,950. All right, so that's going to lead us into our notes for today. We're talking about arithmetic sequences and partial sums. So we just ended up doing a partial sum. We'll talk more about that in a little bit. But an arithmetic sequence is a specific type of sequence. It's a sequence who, when you compare consecutive terms, so one term to the next, always has the same difference or a common difference. So when I look at, say, the first two terms together, when I subtract them, difference between the second term and the first, a sub 2 and a sub 1, that's going to be the same as the difference between the third and the second term, and the fourth and the third term, and the fifth and the fourth term, and on and on and on. It's going to be what we call our common difference. We use the variable d to represent that, but it's going to be the same every single time. So we're either adding the same number each time or we're subtracting. So we have a couple examples down here of sequences, and we want to determine which ones are arithmetic and which ones are not. So we're going to try and determine which ones have a common difference and which ones don't. So if I look at my first example here, my sequence, 3, 5, 7, 9, 11, I want to look at my differences. To get from 3 to 5, we add 2. That is 5 minus 3 equals 2. That's why it's called a difference, because it's the difference between your terms. If I do 5 to 7, that's also a difference of positive 2. 7 minus 5 is 2. 7 to 9, that's also 2. 9 to 11, that's 2. So we have a common difference d of 2. So yes, this is arithmetic. If I look at the second example, however, negative 3, 6, negative 9, 12, negative 15, the difference between negative 3 and 6, or 6 minus negative 3, is a plus 9. To get from negative 3 to 6, we have to add 9. To get from 6 to negative 9, however, negative 9 minus 6, that's negative 15. So I don't even really need to check my other pairs. I could. This is going to be a plus 21 and then a negative 37. But once I see that these two right here are not the same difference, I cannot have a common difference for all of my things, all of my consecutive terms. So we say this is not arithmetic. And the reason for that would be there is no common difference. Okay, so it's not arithmetic, no common difference is the reason why. If I look at C, 3, 6, 12, 24, 48, again, 3 to 6, we add 3. 6 to 12, we add 6. I don't even need to check anymore. I already know no common difference, not arithmetic. All right, so checking if they're arithmetic or not, we're looking for that common difference. So you can do these next 3 examples. Go ahead, you can pause the video, try them on your own, and then come back and check. So if you've got, in this first one, we're going to be subtracting 5 each time. So our common difference D is indeed a common difference. That is negative 5. So this is arithmetic. In example E, we add 2, and then we add 3, and then we add 4. So there's no common difference. So it's not arithmetic. And then the last example is also not arithmetic. Same reason why, still no common difference. And if you look, again, you can check the first 2 sets of consecutive terms. We added 3, and then we added 5. I don't need to check any further past that. So our only 2 arithmetic sequences in all 6 of these examples are A and D. Now, arithmetic sequences are sequences, so they do have an a sub n rule or a way to write the a sub n term, and there is actually a formula for the arithmetic sequence a sub nth term, or nth term of an arithmetic sequence. But this isn't a formula that we just get to use. What we're going to do is we are going to actually derive this formula, which means we are going to formulate it. We're gonna pull it out of thin air, essentially, is what we're gonna do. Is we're gonna build it up, and anytime you want to use this formula on a worksheet that you're turning in, a quiz, a test, you have to derive it. You don't get to just use it. You have to build this formula. So what we're going to do is we're essentially writing a proof of this arithmetic, this nth term of an arithmetic sequence. So whenever we do a proof, we always start with a fact, something that we get to use, and we're going to build from there. So our fact that we're going to start off with is the fact that a sub 1 is equal to a sub 1. Okay, nothing groundbreaking there, but we get to start from there. And then we're also going to use the fact that this is arithmetic. And just like we talked about all up here, all of our arithmetic terms have to have a common difference d. And to get from the first term to the second term, we add d. To get from the second term to the third term, we add d. Third to fourth, add d. So we're constantly adding d to get from one term to the next. So what I want to do is I want to rewrite, or I want to write my a sub 2, my second term, in terms of my first. So to get to my second term, we're going to take the first term and add d. And I want to do the same thing for my third term. Now to get my third term, I'm going to take my second term, the term right before it, and add d. But what I want to do is I actually want to go one step further. I want to say, okay, well, we just said that a sub 2 is actually a sub 1 plus d. So I'm going to take this a sub 2 and I'm going to do a little bit of substitution. So I'm going to say, well, a sub 3, that's actually a sub 1 plus d for a sub 2 plus d again, or a sub 1 plus 2d. Okay, 3 terms is nice, 4 terms is even nicer, so we'll do it for fourth term. This is a sub 3 plus d, but we just said that a sub 3 is really a sub 1 plus 2d. So this is really a sub 1 plus 2d plus another d, or this is really a sub 1 plus 3d. All right, so we have our first 4 terms. We want to write a general formula. We want to write the a sub nth term. So what we're going to do is we're going to look at our first 4 terms. All 4 of these terms, a sub 1, a sub 2, a sub 3, a sub 4, in the final ways that I wrote them, they all have an a sub 1. So it wouldn't be the craziest thing to say a sub n is probably going to start with a sub 1. And then we're going to add to that. We need to figure out what we're going to add to that. So we're going to look at our different terms here. We're going to look at a sub 1. We're not adding anything to a sub 1 to get a sub 1. So that one's not going to be the most helpful. But if I look at a sub 2, I want to add 1d. One of my common differences. I want to add that to get a sub 2. To get a sub 3, we're going to add 2 of our common differences. To a sub 4, we're going to add 3 of our common differences. So each time we're adding 1 less than our n value of our common differences, we're going to add n minus 1 plus d. This right here is our nth term of our geometric series. This is our formula, and we have just derived it. So it's written out nice and wonderfully and pretty down below, but that is the same formula. That is our nth term of our arithmetic sequence. Anytime you are going to use this, on a quiz, test, to use this, you must derive it. Now, you only have to derive it once for each quiz or each test, each thing that you turn in. You must derive the formula, but you only have to derive it once. After you derive the formula once on a quiz, you get to use it as many times as you want on the quiz. You can use it 2, 3, 4, 7, 29 times. You should never have to use it 29 times on one single quiz, but you could. So you must derive this. You must develop this formula on any quiz, test, worksheet that you're going to turn in for homework in order to use the formula. You have to derive it once, but then you can use it as many times as you want on that particular assessment. Going forward, each new assessment, you have to rederive it. So you need to know how to build this formula, just like we did here. But we've already derived it, so we get to use it. So we're going to do a couple examples. We're going to use our formula, and I'm just going to rewrite it. A sub n equals a sub 1 plus n minus 1 times d, where d is our common difference and a sub 1 is our first term. We're going to write some formulas. Now, in the first example, they tell us our common difference is -4 and our a sub 1 is -13. There's not a whole lot to do except for to put them in the right spots. This means our nth term of our arithmetic sequence is -13 plus n minus 1 times -4. Example B, we have to do a little bit more work. They do pretty much, they don't explicitly say it, but they do pretty much tell us a sub 1 is 11, because remember a sub 1, that's our first term. So a sub 1 is 11. We have to figure out what our common difference is, but we're just going to look, okay, what's the difference between 11 and 15? Well, that's plus 4. 15 and 19, plus 4. 19 and 23, plus 4. 23, 27, plus 4. Our common difference is positive 4. Again, we've already derived this formula. We did it just up above. So a sub n is equal to 11 plus n minus 1 times 4. Now, our third example here is a little bit more, potentially confusing because of the choice of variables. This a is just representing any variable. It is not a particular a sub. It's not a term. So let's try not to, hopefully that doesn't confuse us too much. But again, we get to start with, okay, a sub 1, our first term is just a. To look at our common difference, what do you do to get from a to a minus a plus 2? Or a plus 2 minus a, well, that's just 2. A plus 2 to a plus 4, we added another 2. A plus 4 to a plus 6, we added another 2. So our common difference, d, is 2. So our formula for a sub n, our nth term of our arithmetic sequence, is going to be a plus n minus 1 times 2. All right, so again, we've already derived our formula. We did it up here. So we've derived it. We get to use it. If we started a new assessment, a new quiz, a new test, a new worksheet, we have to rederive the formula in order to use it. Now, we're going to use it down in example 3 as well. What we want to do is we want to find the 29th term of an arithmetic sequence. We are told the 5th term is 25 and the 11th term is 55. So this is another way of saying a sub 5 equals 25 and a sub 11 equals 55. And there are a couple different ways that you can go about doing this problem. What we're going to use is we're going to utilize our systems knowledge, the fact that we can solve a systems of equation fairly quickly using our matrices or substitution or elimination. We're going to utilize the matrices to help us on this one. So in order to do that, we need to write a system of equations. So we're going to use that a sub n formula that we have up above. And we're going to write it twice. One where n is 5 and one where n is 11. Now, if n is 5, we already know that a sub n is 25. A sub 5 is equal to 25. But 25, according to our formula, has to equal a sub 1 plus n minus 1. For us, that's 5 minus 1, or 4 times d. And then we do it again with a sub 11. A sub 11, we know that a sub 11 is 55, but that, according to our formula, is a sub 1 plus 11 minus 1, or 10 times d. So we have a system of equations with our variables that's a sub 1 and d. So what we can do is we can put this in matrix form. We can ref a matrix where it goes 1, 4, 25. So constants, I'm just moving them to the other side. I'm rewriting this as equals 25 equals 55 and erasing, just so it's a little bit more consistent with what we've seen in the past. 1, 10, 55 is that second row. We ref this, and we get back 1, 0, 5, 0, 1, 5, which says a sub 1, 5, d is 5. So our formula, our nth term, is a sub n equals 5 plus n minus 1 times 5. Whew. But we've written our nth term, or we've written our rule essentially for our arithmetic sequence. So now when it says, okay, take that, find the 29th term, it says, well, okay, if n is 29, we're asking for a sub 29. That's 5 plus 29 minus 1, or 28, times 5. That tells me my 29th term is 145. Oops, wrote that wrong. That should be a 25, shouldn't it? A sub 29 is 145. Okay, so again, we derived our formula up above. We get to use it all we want at this setting. When we move on to our homework, quiz, or test, we have to rederive it in order to use it. Now, when we talked about sequences the other day, we mentioned that you can sum them up, and we did that earlier today. We summed up a sequence, a couple different ones. We summed one up that was in summation notation, then we summed up the numbers 1 through 29. And we used sort of a shortcut in that second one, but there is, if we are doing a finite arithmetic sequence, okay, so we have a set starting and stopping point. This isn't an infinite one, but if we have a finite arithmetic sequence, we do have what's called a partial sum formula. And so we're going to use that just like we did with our nth term of our arithmetic sequence. We are going to derive that partial sum formula. Okay, so we're going to derive this just like we did our nth term formula, and just like with our nth term formula, anytime you want to use this on a quiz, a test, your worksheet, you must derive this formula. Okay, so I'm just going to write that down there. You must rederive it, derive this formula on any quiz, test, etc. in order to use it. Okay, you can't just say, oh, here's the formula. In order to use it, you have to derive it. So there's a couple things going on, and I'm going to use my colors. So I apologize that things are going to be popping up quite often. We're going to start by, okay, well, just a little notation thing. When we talk about a partial sum, we're going to use this notation, S sub n. This is the sum of the first n terms. Okay, so I'm going to take my S sub n, and I'm just going to write out what this means. So I'm writing out my sum, my partial sum of my n terms. This is just a sub 1 plus a sub 2 plus a sub 3 plus all my terms out to a sub n. Okay, so it's all of those terms out to a sub n. What I'm going to do is I'm actually going to take that formula and I'm going to tweak it slightly, that equation, and I'm going to tweak it just a little bit by using what we did all the way up here, how we rewrote a sub 1, a sub 2, a sub 3, a sub 4, we're going to actually do that in this formula here. So my a sub 1, that stays the same, but my a sub 2, we said that we could rewrite that as actually a sub 1 plus d. And then a sub 3, we said that was really a sub 1 plus 2d. And we go all the way out, and then that a sub n formula, we said that was a sub 1 plus n minus 1 times d. Okay, so we're doing this. Got that. I'm going to actually write out my S sub n formula. I'm going to write it out another way. So we did, we got pink and a little bit of red there. I'm going to do some blues. What I'm going to do is I'm going to take that partial sum and I'm going to rewrite it. And what I'm going to do is I'm going to use the fact that when I add, it does not matter the order that I add my numbers in. So when I rewrite this partial sum, I'm actually going to write it by starting with a sub n. Then we're going to add to that a sub n minus 1, the term right before it. And then a sub n minus 2. And then we're going to go all the way out to a sub 1. So a sub 1 is going to be at the end of our list instead of at the beginning. It's okay. Addition doesn't matter the order. That's the commutative property. It's a wonderful property. And just like we did, I'm going to take this and I'm going to tweak it slightly. And I'm going to tweak it in a very similar way, but a little bit different. Now, we said that we could rewrite a sub 2 right here as this a sub 1 plus d because we took the previous term and we added our common difference. What I'm going to do is I'm going to take that same idea, but I'm going to just think about it in a slightly different way. So I'm going to start with a sub n. That's same as it always is. But my a sub n minus 1, to go backwards in my sequence, I don't want to add d. If I'm starting at like the 10th term and I want to go back to the 9th term, instead of adding my common difference, I'm actually going to subtract it. So a sub n minus 1 is a sub n minus my common difference of d. And then a sub n minus 2, that's a sub n minus 2 of my common differences of d. And I keep going down in that way right there. And I want to get to a sub 1. And so to get to a sub 1, that's actually going to be a sub n minus 1 of my common difference of d. And that idea right there, you can actually get that from our a sub n formula. All right, so I'm going to erase this in just a second. But if I start with a sub n equals a sub 1 plus n minus 1 times d, if I want to solve that for a sub 1, which is what we're trying to do, we're trying to rewrite a sub 1, our first term. To get this a sub 1 alone, I'm going to subtract the n minus 1. So this is a sub n minus n minus 1 times d equals a sub 1. So that's what we did. We did this substitution right there. Okay, so we've got a bunch of equations. They're all equal to our partial sum. So we just wrote f sub n 4 completely different ways. And we're going to actually utilize it. So what I'm going to do is I'm going to look at this equation here, this dark the red one there, and then this light blue one. And what I'm going to do is I'm actually going to add those two equations together. So we are allowed to add equations. We can add the left sides and we can add the right sides. If I add the left sides, I have an s sub n plus an s sub n. So that's 2s sub n. I'm actually going to slide this over just a little bit so I can keep my ordering the same. And again, I'm adding this equation here with this equation here. And all we're going to do is we're going to go term by term. So if I look at the first two here, that's just going to give me a sub 1 plus a sub n. If I look at the second one here, what's going to happen with the plus d and the minus d? They're going to cancel, and I'm left with a sub 1 plus a sub n. And then my third terms, now my plus 2d and my minus 2d, those are going to cancel, and I'm left with another a sub 1 plus a sub n plus dot 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 plus these last ones, positive n minus 1d, negative n minus 1d, those cancel. I'm left with another a sub 1 plus a sub n. So if you think back to the jack problem, he had to add up 1 to 90 times. What we did was we took the first number 1 and the last number 99, we paired them up. We paired up all the ones in between, and they all paired up to be the same value. So we do this, we count up how many pairs. How many pairs did we have? Remember, these are all, we had the same number of terms each time. Each one we had n terms, n terms, n terms. So there are n of these a sub 1 plus a sub n's. So I can say, well, this 2s sub n is equal to n times a plus 1 times a sub n, which means to get s sub n alone, we're going to divide. I get n minus over 2 times a sub 1 plus a sub n. And that right there is our formula for partial sums of finite arithmetic sequences. So I have it written down below, nice and pretty. Finite arithmetic, little typo there, that should be an A, arithmetic sequence with n terms. S sub n is n over 2 times a sub 1 plus a sub n. Another typo, a sub n. Take our first term and our second term, or last term. First term and our last term. So we did that to the 1 plus 99, 2 plus 98. They all were 100, and then we had 50 of them. So the n over 2, that's where that's going to take into account, because if we had 99, the n over 2 is really 49.5. So it wasn't really 50 of them. That was the 49 whole 100s plus half of the 100, that 50 alone. So we're going to use this. Example 4, we're going to find the sum of the first 50 multiples of 7. Think about 50 multiples of 7. Multiples of 7, we're adding another 7 each time. So like when n is equal to 1, a sub n is 7. When n is 2, 14. When n is 3, 21. So for this, our a sub n formula, our common difference d is 7. And our a sub 1 is 7, so this is 7 plus n minus 1 times 7. A sub 50 is 7 plus 50 minus 1, 49 times 7. That's 350. Again, we've already derived this formula, so we get to use it on any quiz or test. You have to reproduce this. You have to derive this before you can use it. But since we've already derived it, we are allowed to use it. We can say, well, our s sub 50 is 50 over 2 times our first term of 7 plus our last term of 350. So this is 25 times 357. Or our total sum is 8,925. Example 5, we're going to find the 150th partial sum of the sequence. And this is where having this formula is really handy, because I don't want to write out 150 terms and then add them all together. So this is the sequence, this formula is really helpful in saving us some time. I do need to be able to determine what the 150th term is, so I'm going to start by writing my formula. I'm going to find my common difference. Each of these, I'm adding 11 each time. So our common difference here is 11. A sub 1 is 5. So I can write my nth term, my a sub n is 5, plus n minus 1 times 11. If I'm looking for the 150th partial sum, I need to know what a 150 is. So 5 plus 150 minus 1 is 149 times 11. That is 1,644. So the first term of our sum is 5. The last term of our series is 1,644. We want to add up all of the numbers in between. There's 5, 16, 29, and 38. So S sub 150 is 150 over 2 times 5 plus 1644 gives me 75 times 1649, or 123,675. Whew, very glad I didn't have to add up all those numbers by hand. All right, 2 more examples. Example 6 here, we're finding our sum. Now this is written in our summation notation. So we are adding from n equals 1 to 100. So this is asking us to find S sub 100, our 100th partial sum. That's what this is looking for. But the way our formula is written is currently not in our nth form of an arithmetic sequence. All right, so what I want to do is I want to rewrite this so it's in our nth term formula. So I'm going to look at my n values and my a sub n values, and I'm going to set this up. So when n is equal to 1, we still can use this to produce our a sub n values. It's just not in that a sub 1 plus n minus 1 times d format that we want to use. So when n is 1, a sub n, our first term, is actually 5. When n is 2, our second term is 8. When n is 3, our third term is 11, and so on and so forth. You can see that our common difference is 3. So d is 3, and our first term, a sub 1, is 5. So that means a sub n is 5 plus n minus 1 times 3. So using that, we can get our 100th term, and we could have actually gotten our 100th term from here, but we do want to get practice. We do want to practice and get good at rewriting this in our a sub n format. This is 5 plus 100 minus 1 is 99 times 3, or 302. So our 100th partial sum, or S sub 100, is going to equal 100 over 2 times 5 plus 302, which is 50 times 307, or 15,350. All right. Last example, a little bit more of an application type problem. We have an auditorium. It has 20 rows of seats. There are 20 seats in row 1, 21 seats in row 2, 22 seats in row 3, so on and so forth. What is the seating capacity of the auditorium? So let's practice. Let's write this in our a sub n format. Let's look at our n's and our a sub n's. Our n's are going to be the row number, and a sub n is going to be the number of seats in that row. So in our first row, we have 20 seats. Second row, 21. Third row, 22, so on and so forth. We can see that our common difference here is going to be a 1. A sub 1 is equal to 20. So a sub n is 20 plus n minus 1 times 1, or 20 plus n minus 1. We don't have to multiply by 1 if we don't want to. So our 20th row is going to have 39 seats. So S sub n, remember that's the formula, n over 2 times a sub 1 plus a sub n. We've already derived it, so we get to use it. S sub 20 is 20 over 2 times 20 plus 39, or 590 seats. Okay, so arithmetic sequences, we have an a sub n rule and we have a partial sum rule. In order to use those, you have to derive them. So you do need to know both of these proofs, and you do need to be able to reproduce both of these proofs on any quiz, test, homework worksheet. Anytime you want to use either of those two formulas, you have to be able to derive it.